Hello everyone, so welcome for today's session in the another video. So in the last video we had discussed about the quantum mechanics, the basic differences, and we had also discussed about the canonical conjugate variables, and we have shown that in the canonical conjugate variables pairs, so where we had taken the two pairs, one is the first pair is the momentum and the position. So with the uncertainty principle of Heisenberg, so it is not possible to define the momentum and the position at the same time, means instantaneously we cannot define both position and momentum, whereas even the energy and the time cannot be defined at the same time. So that is what we have concluded with the last session. So now let us switch to our screen and see the basic postulates of this quantum mechanics, which are developed by the two scientists with a different way, but the final approach was the same ultimately towards the quantum mechanics. So one is the Schrodinger, who defines the wave mechanics, and the other person is the Werner Heisenberg, who has defined the matrix mechanics in the form of matrix. So let us switch to the screen and see it. Okay, so now let us see the basic postulates here. So as I told you, these basic postulates are developed by the basic principle of the quantum mechanics was developed by the two people, that is the Schrodinger and the Heisenberg. So the first one is the Schrodinger. So that is based on the wave mechanics. The approaches were different, but they are related approaches. And the second is the Werner Heisenberg. So he is defined in terms of the matrix mechanics in the form of matrix. We'll go for this simplest method of defining the Schrodinger wave equation, because this matrix mechanics is beyond the scope of our tutorial. So now we'll consider the first one, that is the Schrodinger wave equation. Before going to the Schrodinger wave equation, we'll talk about the basic postulates which are defined by the Schrodinger based on the wave theory, and that is based on, so Schrodinger equations are based on two things, or it was developed on the idea of, that is the Planck's quantum theory plus de Broglie's wave equation. De Broglie's wave equation. So with these ideas, the Schrodinger has developed the postulates, the quantum mechanics. So before going to the postulates, now let us discuss the basics of this. So here we have to do some considerations. So let us consider an object to be as the physical system, and the collection of all these physical systems, like all these, let me call this as PS, here PS, and collection of all these physical systems are called as an ensemble. Let me write neatly here. These are called as ensembles. Okay, and these have certain properties, like the system has certain properties, like it has the properties of the position, it has the property of momentum, and it has the property of the energy. And all these properties of the system are associated to the system. So all these are associated to the system, and These are called as the dynamical variables. These are called as the dynamical variables, or it is also called as the observables. Okay. So in quantum mechanics, in classical mechanics, I'll just write in short. So the state of the system is defined by these dynamical variables. The state of the system is defined, that is, let me write like this, is defined by these dynamical variables. Whereas in classical mechanics, whereas in case of the quantum mechanics, the state of the system is defined by, it is defined by a state function, and that is represented by psi. So that is the basic difference. Again, one more difference between the classical mechanics and the quantum mechanics. So in classical mechanics, the state of the system is defined by the dynamical variables. So the dynamical variables is nothing but these positions, momentum and energy, whereas in the quantum mechanics, the state of the system is defined by the state function itself, that is psi, and that will give all the information that is required. So in quantum mechanics, the state of the system with a number of particles at any time is defined by designating the position and the momentum coordinates of all particles at that time. Whereas in case of quantum mechanics, we follow the rules, the different situations, and also provide us with rules for extracting the useful information from given psi. So here it follows the postulates. So now to continue with the postulates, we consider one coordinate. We will consider only one coordinate x with time t. So with this, let us go with the first postulate. So the first postulate states that there exists a state function psi of x comma t which contains all measurable information about each particle of a physical system with an operator, with a mathematical operator. So that can be in either addition, multiplication or differentiation. So let us write here the first postulate. So there exists the state function, that is state function. Remember, always the state function is defined by psi of x comma t, because only we are taking the one coordinate here, so which contains all the measurable information, measurable information about each particle of a physical system, and that is defined by an operator, and that is specified by an operator. So here with the mathematical operator we can have either an addition, multiplication, or we can have the division operators. So the division operator, just for an example, that can be represented by a partial derivative with respect to x. So this is nothing but the differential operator. So this is the first postulate. It means you can extract the information, measurable information of any particle in the physical system by the existing state function by using these operators. And the second postulate is so every dynamic variable which we have discussed corresponds to one operator. Every dynamical variable has a corresponding operator, and this operator is used on the state function to obtain the measurable informations. So now let us see which are those operators which are used on these dynamical variables. Now I'll make it 2 columns here. So dynamical variable, and the second one is the quantum mechanical operator. So if we take the first dynamical variable, that is position, and let us define this position as x, then its operator is represented as x hat, which is equivalent to x. And the second dynamical variable here, let us consider this as the momentum as px. The reason of writing this px as we are defining in only one coordinate system here, that is why it is with respect to x, one particular coordinate. If you are talking about the 3 dimension, then it's supposed to be p of x, y, z. So then its operator, the quantum mechanical operator, that can be written as p x hat, which is equivalent to h hat by j with a partial derivative with respect to that particular coordinate, that is x. And then the total energy E is operator, which is equivalent to E hat, is equivalent to minus h hat by j, partial derivative of with respect to time t. And there is one more dynamical variable that we can consider, that is the potential energy, that is represented as V of x. Then the V hat is equivalent to V of x. Let us call all these with certain equation number here. We are continuing with the previous video tutorial. There we had the 2 equations, equation 1 and 2. Let us call this as equation number 3. Now here h hat is nothing but it is h by 2 pi. It can also be written like this, in short, the h hat, which is equal to h by 2 pi. So this specifies that h hat is used to quantify the significance, the h hat is used on the quantity, signifies the operator corresponding to that quantity. So to signify the operator corresponding to that quantity, we use this h hat. So if an operator is applied to this state function, what happens? Let's see. If an operator y hat acting on state function psi produces a linear homogeneous equation. So what is that linear homogeneous equation? So here y hat when it is operated with psi, which will result in again just y into psi. Let us call this as 4. So homogeneous equation is nothing but, I'll just explain you with the other terms. So if we have, say, the two objects here, say x1, which is multiplied by a constant, and then there is a one more an object, say x2, which is multiplied by another constant, which should be uh, equal to a, the same constant a, it should be equal to the sum of the two objects, and then it is multiplied. So if it is the right hand side and the left hand side results in same solution, so such solutions we call it as the linear homogeneous solutions or the equations. Okay, so now looking at the equation 4, so looking at the equation 4, here y is a real number, therefore a y is called as the eigenvalue, and this function we call this as eigenfunction. Now let us talk about the third postulate. So third postulate states that there are two things which it states. So the first one is that the state function psi of x comma t and its derivative and its space derivative with respect to x must be continuous. And finite. It must be continuous, it must be finite, and single valued for all values of x. So that is what the postulate 3 states. There are two things again in postulate 3. So one is that the state function with respect to only one coordinate, that is psi of x comma t, and its space derivative with respect to x must be continuous, finite, and single value for all values of x. And second point in the postulate 3 is the function or the state function psi must be normalized. It must be normalized. So now to prove this, so first condition of this third postulate, so then it means that the physical system should meet, the requirement of the physical system should meet. It means the no state function of the physical system in the real world can be an infinite. It has to be a finite physical system. So it should be a finite physical system. And to prove with the normalization, so here basically the state function with its complex conjugate, so this we call it as the probability density. This we call it as a probability density, and the probability density states that the probability of finding the particle within all space should be equal to 1. So the probability of finding the particle in all space should be equal to 1, and for normalization condition we need to integrate this. So if we integrate this probability density, psi with its psi conjugate with respect to dx should result in 1. So let us call this as equation number 5. So same thing if we represent in the three-dimensional case, so then we get this as 3 integrals for the three-dimensional case. So let me write here, this is for three-dimension case. So then it is a triple integral with the psi conjugate into d tau in this case, which is equal to 1. So here d tau represents in terms of volume, the representation of an element of volume about the point where psi and psi conjugate are determined. Okay, so this is about the third postulate. So moving on to postulate 4. So postulate 4 talk about the average of the dynamical variables. So it is about the average represent as y of any dynamical variable corresponding to, that is corresponding to the state function, corresponding to the state function psi. Therefore, the average of the dynamical variable can be represented by an integral of minus infinity to plus infinity with the conjugate of the state function and the y hat, the operator applied to the state function, into dx. So let us call this as equation number 7. So this is our equation number 6 here. So that one is 7. So here psi is assumed to be normalized. The state function is assumed to be normalized. So this equation gives us the important relation between to calculate the observable quantities that we can compare with the measurements. Now moving on to postulate 5. So postulate 5 talk about the operator for any measurement for which the operator is not postulated is determined by expressing the measured quantities in terms of 4 basic variables, as which we have discussed in equation number 3. So equation 3 is nothing but these things, the operators which we have defined here. So these things, and substituting the operator to these variables. Then the state function describing the particles generally in a form of wave, and these are called as the wave functions, and the field of the quantum mechanics is known as the wave mechanics. So here basically what we are doing is that the operator for the measurement which is not postulated is determined by expressing the measurement quantities in any of these 4 basic variables by substituting the operator for these variables, and these we call it as the wave functions and the wave mechanics. And if we interpret the psi function with its psi conjugate into d tau, so this represents the statistical probability that the particle is found in a volume element d tau at any instant of time. So it means a particle can be found in a volume element d tau at any instant of time, and this can also be considered as psi with its psi conjugate, just with this as the probability density, as I told you before, the probability density. So it states the probability of finding the particle within all space is equal to 1. So this should be equal to 1. So that's it about this tutorial. So we have talked about the basic postulates. So in the next tutorial we will going to talk about the Schrodinger wave equations and its applications. So thank you.